Okay. It's 8:02. I'm going to start. I introduced myself before. My name is Kim Martini. I'm the senior oceanographer at Seabird Scientific, and welcome to Seabird University. I'll be teaching this with Greg Ikeda. We've both been teaching this for several years now, and we're really happy that we can do this online and reach a lot of people. So next slide, please, Greg. So some virtual Seabird University basics. We are using Teams Live. You can see us, but we can't see you. So this is just a different kind of platform. If you have any questions, there's a chat button in the upper part of your screen. Please say hello if you're on there. So it's great to see who's up there. And also, if you need closed captioning, you can turn them on in the settings up there. All right, next slide, Greg. All right, so important Teams Live, just to do that here, I'll show you how to do it right here. In the upper right-hand corner of the screen, there is a there's a little question mark. If you have questions, you can ask them in there. And if you want to turn on closed captioning, you go down to the settings and you can turn it on through there. So if you're there, say hi in the chat or ask a question. So we'd love to hear from you as well. And, oh, good. Lots of people there. Okay, great. Can't always see everything that's on there. Okay, so this is our schedule for the week. For week one, we're going to do, it's going to be Greg teaching. So it's Tuesday, October 5th. So that's today. We're starting at 8 a.m. He'll be teaching today profiling with and without a winch, the 19V plus V2. On Thursday of this week, he'll be teaching capturing water on small boats. So that's all about water sampling using the SBE 55. And then we're going to take a week off and we're going to come back and I'll be teaching starting Tuesday, October 19th. I'll be talking about moored instruments. So we're going to talk about how to deploy and recover with the SBE 37 microcat CTDs and assorted instruments. And then on Thursday, I'll be talking about nitrate monitoring. So using that in the moored mode. All right. Next slide, please, Greg. Okay, so how long is the class? It's an hour plus about 30 minutes for questions and answers and review. Please ask questions during the class. Yes, you can. I'll be monitoring the chat as well during this. So if you have any that come up, Greg can either answer them or I can answer them. If you have any additional questions after this, we have a great tech support team. So you can either reach them through email or through the phone. So they deal with they know all about our instruments, how they're deployed, and how to help you with your information. And then this is a course, and so if you miss something, can you watch this again later? Yes, we will post the recorded sessions at the end of October. So if there's something you missed, you can see it again later. All right. Okay, so next slide, Greg. So we meet the instructor. So me, I've kind of introduced myself already. I'm Dr. Kim Martini. I'm a senior oceanographer here. I deal a lot with sensor technology and how they perform and how to build them better. So really the nuts and bolts of how the physics of our sensors work. I've been over with Seabird for over 5 years. I've been a Seabird scientific user of their products for over 17 years, and I've spent over 100 days at sea. So teaching from not only from being in the company, from being a person that actually deploys these in the field. What aspect of the ocean scares me? This is kind of our teaser question. It's kind of a running joke around Seabird that I do not like horseshoe crabs. I have an irrational fear of them growing up from when I was little, growing up in the East Coast. So they like to get me things about horseshoe crabs. And next, I think I'm gonna let Greg introduce himself, but he's pretty awesome. So I'll let him go.
Okay, thanks, Kim. Hi, everybody. My name is Greg Ikeda. I will be your instructor for today. So I've been at Seabird Scientific for about 6+ years or so. And prior to that, I spent a lot of time on research vessels out in the field using Seabird Scientific equipment. So at this point, I'm pretty familiar with this stuff. I started off in technical support at Seabird, so there's a good chance that I may have talked to some of you on the phone or via email if you had any technical issues that popped up. I'm the Senior Content Development Manager here at Seabird Scientific, so trying to leverage that technical support background to create marketing material that is not just flashy marketing material, but actually has some value to the scientific community. We're always open to case studies, and anytime you want to share your data with us, we would love to see it. What aspect of the ocean scares me is big waves. Even medium-sized waves, I think, are pretty scary. I've been a surfer for a little while, and there's a certain point where I just decide I'm not going to get in the water because the waves are a little bit too scary. Okay, so let's jump into it. Today, we are talking about the 19 plus V2. That's this instrument that I have right in front of me. As Kim alluded to, we're trying something a little different this year with Seabird University. In the past, we used to have people fly out to Bellevue, Washington, and sit in a hotel conference room with us while we just blasted them with general information about the entire Seabird product lines. That's helpful for some people, but in many cases, not everybody is using everything that we sell. And so we want to try to break up our Seabird University sessions into focused classes that focus on specific product families, specific applications. So we'll be putting a survey into the chat here. We would love for you to fill it out and tell us what kind of topics you're interested beyond the 4 topics that we're going to be covering in October, so that we can provide more training material for all of you. But today we are talking about the 19 plus V2. Just a little background, what we're going to do here is I'll be showing some PowerPoint slides with some information about this instrument. I'll go to a physical overview talking about the instrument that I have right in front of me. And then I'm going to demonstrate some of the software that you use to communicate with the 19 plus V2, configure it to go out in the field, upload data, process your data, visualize your data in real time. We offer a lot of software tools that I want to show you today. And then at the end of this presentation, I'll be going through some sort of general maintenance and troubleshooting techniques for figuring out why you might not be able to communicate with your instrument and determine whether or not it's ready to go out in the field. But let's start from the top. The 19 plus V2 is a dual profiling and moored CTD. For the context of this presentation, it will be mostly talking about the profiling aspects of this instrument. But you can configure this to be a moored CTD. When you do that, it's very similar to the 16 plus V2 moored CTD that we sell here at Seabird. It has integrated temperature, conductivity, and pressure sensors, internal memory, and the ability to output data in real time. And it also has internal batteries and can accept external power. Takeaway point, the 19 plus V2 is a pretty light, very flexible platform for people to use for profiling applications, moored applications. If you do or do not have the ability to transmit data in real time, you can also integrate this with a water sampler, which I will be talking about and demonstrating on Thursday with the SBE 55. This instrument can support up to 6 analog sensors. On the right here, we have a diagram of the connectors on the 19 plus V2. By analog sensors, we mean a auxiliary sensor that has a 0 to 5 volt output. Essentially, the 19 plus V2 can take in that voltage, log it to its memory, or output that in real time, and we can use software to then convert the voltage from that sensor, for instance, this SBE 43 oxygen sensor, into engineering units, milliliters per liter of oxygen, chlorophyll, etc. It's also capable of supporting one RS-232 sensor, although it does not support the entire selection of RS-232 sensors out there in the world. It can support any of the instruments in this list here. We won't really be going into that too much, but if you have questions about that, please put it into the Q&A. And Kim, can you tell me if the slides are keeping up with my presentation? There might be some lag here.
Will do.
Okay, thanks. Okay, so now we're going to go into a little physical overview of the instruments. I'm going to switch my camera over, so please bear with me for a moment. Okay, Kim and Lindsay, can you see that?
Yes, we can.
Okay, great. So I've got this camera on this little dolly here and the 19 plus V2 in front of me right now. So I'm just going to go through sort of the nuts and bolts on the outside here, and I'll demonstrate how to replace the batteries on this unit. So first of all, let's start on this side. This is what we call the connector end cap, and this is where all of the communication happens. So on the connector end cap, we have a spot to plug in.
You're going to want to pause your videos just going in and out.
Okay. Unfortunate. Okay, please bear with us. Okay, so any of the attendees, can you please tell us in the chat whether or not you're able to see the video? It seems like we might be having some network problems. I promise we tested this in advance, but it's raining pretty hard in Washington right now, so maybe that has something to do with it. Kim, Lindsay,
I think we can see the front end of that right now.
Okay. Okay, so unfortunately, it seems like the video may or may not be keeping up, but we'll do our best to keep with it. So right now, hopefully, you're looking at the connector end cap of the 19 plus V2. So this is where all the communication happens. This is where you would plug in the cable to communicate with your CTD. This is where you would plug in your auxiliary voltage sensors, and we saw the connector diagram back there, and I will demonstrate that in a little bit more. And this is where you would plug in your RS-232 sensor if you're using one. In the middle here, if you can see it, you also have the pressure ports. That is where the input for the pressure sensor is able to sense pressure, hydrostatic pressure from the water. Moving onward, we have this metal guard right here. This is known as the cell guard. On top of this, you'll notice this has an on-off switch. So this doesn't turn the instrument on or off necessarily. When it has power, when it has batteries installed, it's essentially always on and only in sort of a quiescent sleep mode. This on-off switch is going to tell it to start or stop sampling. So as long as this is configured properly, you do not need to hook your CTD up to a computer and to tell it to start logging. All you have to do, flip the switch to on, and then it's ready to deploy.
Hey Greg, I can see
ahead.
that it's not continuing. I can see your video. Sorry to interrupt. I can see it in the little box, but I don't think it's actually broadcasting out. That's the issue.
Okay, it's too bad.
Yeah, it might be an issue with Teams. So.
Okay, that's unfortunate. I'm going to try leaving this call and rejoining. Maybe that will help. Sorry for technical difficulties, everybody. I will be right back.
Thank you for your patience, everyone. Sorry, we are encountering some technical issues, so just bear with us.
Yeah, thanks everyone. I realize that this is a little bit laggy, so it looks like it might be a Teams issue because we can actually see it pretty well down here, so it just might not. He's going to restart to get it broadcasting out. And thanks everyone who gave us a little bit of tips in the chat we can actually see. So we're replying and troubleshooting at the same time. It's always a good time to do your Zoom stretches. I don't know if you have any of those. I will not lead you through them because then you will all know that I cannot touch my toes. So, and also I'd actually end up outside of the screen. So, but thank you again for bearing with us. All right.
Okay.
Here, Greg is back. I'm going to switch over to him. All right, Greg.
Okay, can you see the camera here?
I can, and I see it moving.
Okay, that's good. Okay, apologies for that. I didn't change anything, so it's possible that might happen again. But let's keep going. So last I left off, underneath this cell guard is the conductivity cell and the temperature sensor. And so if we look at it from this angle here by the connector end cap, let's try to lower it down and raise this up. We have the temperature sensor precedes the conductivity cell, and then the conductivity cell is a tube that runs down the length of the cell guard. The conductivity cell itself looks like this. This is actually maybe a microcat conductivity cell, but point is it's a borosilicate glass tube with 3 electrodes inside of it. Because it's glass, it's pretty fragile. This is a precision scientific piece of equipment, and so we want to protect it. So hence the durable metal guard here. Going past that, we see that we have this plumbing, this little piece of Tygon tubing here. And in this case, I have an oxygen sensor installed on my CTD. This is the SBE43. And so we have the plumbing going from the conductivity cell to the oxygen sensor, and then continuing onward to the SBE5 pump here. So what this pump does is it pulls water past the temperature sensor, through the conductivity cell, through the plumbing, through the oxygen sensor, through this plumbing, and then out the exhaust here. It's important that this pump is pulling water and not pushing water, because if it were pushing water and it preceded all the sensors, then the pump would be affecting the sample. However, it's pulling water, so that's not a problem. And so we get really tight alignment between our temperature sensor, our conductivity sensor, our oxygen sensor, and anything else we might have plumbed in there. And now you might also notice we have this little Y fitting right here on the plumbing. This CTD is configured to operate in the vertical orientation. So when we're deploying it, we're holding it up like so, and it's descending through the water column in this orientation here. You can also configure this to be in the horizontal orientation, in which case this Y fitting here is not going to be there. What's important about that Y fitting is that this is a pathway for bubbles to escape from the plumbing here. So if you have bubbles trapped inside of your plumbing, those are going to affect the samples that you get from your CTD. So removing those bubbles is really important. Bubbles want to float upwards, so it's important that the pathway for bubbles to escape is at the highest point in your plumbing. If you deploy this particular CTD in the horizontal orientation, you're not necessarily going to purge all the bubbles because this is not the highest point. This is the highest point. And so you want to reconfigure your plumbing if you're using a deploying this in a horizontal orientation. Kim, how are we doing on the camera right now?
It looks like we're doing really great, and we have confirmation from a lot of people. Thank you very much that it's going. It's a lot clearer now.
Okay, great. Thank you. Okay, awesome. And as mentioned before, the 19 Plus V2 has its own set of internal batteries. And so I'm going to demonstrate how to remove those batteries. There's not too much to it, but there are a couple of things that you want to look out for. So on this side right here, we have the battery end cap. And what a lot of people do, me included, is the first time they try to replace batteries, they try to take out these 2 screws right here because they are obvious and they're screws and you're obviously trying to take it off. That's not actually what you want to do. What we're going to do is screw off this entire end cap by using this piece of plastic as our leverage. So what I like to do is take an adjustable wrench like this, fit it onto this piece of plastic, and then you unscrew it. Lefty loosey, righty tighty. Okay, a couple of things here. We have an O-ring right here and an O-ring on the end cap here. This is obviously a pathway for flooding, so it's very important that these O-rings are in good condition. They don't have any fibers bridging them, and you take good care of them and inspect them before you reinstall the end cap on the CTD. So setting that aside, next thing we see is this battery cover plates, this little green thing. We have 3 screws on this, and so these batteries are held in with springs. And because they're held in with springs, this cover plate has some tension on it. And so you don't want to remove each one of these screws individually. You want to back them out evenly as you go. So I'm going to take my screwdriver. And as I'm backing out the screw, I can see the cover plate kind of pushing outwards. So I'm just doing a few turns at a time. And slowly removing each of these screws. Okay, once those are off, you can reach in here, pull this out. And try not to lose all of your hardware, as I just did. So once you've got the battery cover plate off, you have a spring here and then spots for the batteries to connect. So you'll see this is where the negative battery connects, this one right here, and then your 2 positive ends there. I'm going to set this aside, hunt down all of my hardware. And inside, you have your alkaline D cell batteries. I'm not actually going to take these out. This is pretty standard stuff here. So with the alkaline D cells, you have 3 columns. They fit into a post here. You have 9 batteries inside of the CCAT. And this can get you pretty good deployment endurance. You can get quite a bit of life out of the 9 D cell batteries here. And on top of that, you can also power it externally. So that's how you take off the battery end cap and battery cover plate. It's important that you do it, remove the battery end cap as I demonstrated there, because removing this cover plate 1 screw at a time is going to make it really difficult to take off. To put it back on, you're going to align the spring with the batteries here. And this part can get a little bit difficult. Because these batteries are being pushed out by springs internally, you need to line the screws up with the posts here and then push the cover plate down. In this case, I'm actually going to set this aside because this process takes a little bit, and I'm going to power my CCATs, the 19 plus V2, externally. So I'm just going to put that back on temporarily for now. Set this aside. And grab my DC power supply. So the 19 plus V2 can accept 9 to 28 volts DC. Good rule of thumb is 12. So I have this set for 12 volts. Let's just screw my end cap back on. And to apply this voltage to the 19 plus V2, we're going to apply it to the data I/O cable. So the cable you have probably has these two black and red twisted leads coming off of it. These connect to the power input pins on the 19 plus V2 connectors. So all we have to do is take this, connect positive to red, negative to black, and provide power. At this point, we're providing 12 volts to the 19 plus V2. This is a really useful thing to do if you are testing your unit on the bench, you don't know the life of your batteries, and or if you are deploying this with external power. So right now we've got it going like that. Okay, I'm going to switch back to the presentation, and then we're going to look at some software while it's powered externally like this. While I'm switching back, Kim, Lindsay, if you want to answer any questions or do any tech supports.
Yeah, Greg, we have a question about alkaline batteries. Some of the other instruments use lithium-ion D cells. I actually have to check. I don't know, Greg, do you know that one off the top of your head?
No, actually, that is surprising to me. To my knowledge, we don't use lithium-ion D cells. The 19 plus V2 does have an optional rechargeable battery pack. It's fairly rare in the field these days, but I believe that's a NiCad battery pack, not lithium-ion. You might be confusing it with this battery pack here. So this is the battery pack that goes into SBE 37s. This uses lithium-ion AA cells. These are, I think, 3.6 volt cells, different from standard AA's. Those don't go into the 19 plus V2. It's possible you're thinking about that. That being said, I don't know of any Seabird equipment that uses lithium-ion D cells. While I have this in my hand right here, tech tip is if you have one of these SBE 37 battery packs handy, you can actually use this as a power supply for the 19 plus V2 in a pinch. I don't use it to deploy your instruments, but if you're testing this on a bench and you don't have a nice DC power supply like this, this battery pack provides 14 volts on the two pins on the bottom. So if you can connect to these two pins here, you can get that 14 volts to your 19 plus V2. It makes it handy for testing on the bench if you don't have a dedicated power supply handy. Okay, so we are switching over to the presentation. Okay, great. So with the 19 plus V2, you have a couple of options for deployment. As I mentioned before, it has integrated temperature, conductivity, and pressure sensors, and you can install a handful of external auxiliary sensors to the 19 plus V2. And it also has its own batteries and internal memory. So if your ship, dock, whatever, does not have a conducting C cable, you can deploy this thing on its own, where it's going to log samples to its own memory. You'll upload those later and process them. You're not going to get real-time data. You won't necessarily be able to see thermocline, halocline, etc. But if you're just out there doing several CTD profiles, you can tie a rope to this thing and drop it in the water. That works fine. Alternatively, if you have more equipment on your research vessel, such as a winch and slip ring with a conducting C cable, the 19 plus V2 can be integrated with a water sampler or what's called the PDIM, Power Data Interface Module. In order to communicate in real time, this requires quite a bit more equipment. So on the bottom left, we have our 19 plus V2 measuring temperature, pressure, and conductivity. And then that's connected to an SBE 32 water sampler, SBE 55 water sampler, or the PDIM. That is handling the voltage and converting the RS-232 communication from your CTD to DPSK, sending that up the winch and the slip ring, which then goes to your SBE 33 deck unit, which is handling the power, reconverting that signal from DPSK to RS-232 and sending that data to your computer, which is then running CSAVE or some software that is collecting the data. This is akin to something you might see on a larger research vessel where someone might be using the 9+ profiling CTD. to get real-time data from their instruments. The 19 plus V2 can do a very similar thing if you have the right equipment. Additionally, as I mentioned before, this can be configured to work in moored mode. So when you set it up like that, it emulates the 16 plus V2. You can deploy it with real-time output or store the samples in memory. But it's the same as the profiling version. You're still able to support auxiliary sensors. It can still provide power for those sensors and collect the data, save it in memory or send it in real time. Word of warning, not every auxiliary sensor is made for both profiling and moored applications. For example, the SVE18 pH sensor, not really made to be used in moored applications, really just designed for profiling. So if you have an 18 pH sensor installed on your 19 plus V2, you reconfigure your 19 plus V2 for moored mode. Don't expect to get good pH data for much longer than probably half a day or so. So FYI. Okay, so next we're going to talk about C-term V2. This is the software that you use to talk to your 19 plus V2. This is terminal software made for Seabird Scientific CTDs. You can use a different terminal like PuTTY or TerraTerm to talk to your 19 plus V2. That'll totally work fine. However, C-term V2 has tools built into it for configuring your instrument and uploading data from the instrument. So you can either type commands into the window, or you can send commands automatically from the send commands window on the left. I'll demonstrate that momentarily if you don't necessarily know the commands for your 19 plus V2. So right now we're going to fire up C-term V2 and get into it. Okay, switch over and share. C-term. Okay, so here we have C-term V2, and the first thing we're going to want to do is plug our CTD into the computer. So right now we're powering it externally, 12 volts, and we have our data I/O cable plugged in to this port on the CTD. Hopefully you can see that. The screen is probably pretty small right now. This end of the data I/O cable is what we're going to plug into our computer. And now my laptop does not have a dedicated serial port, so I have to use one of these USB serial dongles. These will allow me to have a serial port on a computer plugged in via USB. Take this guy here. Plug this in. Okay, so one of the first things you're going to want to do is once you plug in a USB serial adapter, if you're using one, is to open your computer's device manager and identify which COM port your computer is assigning to that USB serial adapter. In my case, I've navigated to ports COM and LPT, and I can see that it's communicating on USB serial port COM7. So within C-term, I'm going to specify COM7. I open up my instruments menu here. This is a list of all the instruments that C-term V2 can support, and click on 19 plus V2. That's going to launch the C-term window. Which will allow me to communicate with my 19. Okay, now depending on your setup within C-term, it might connect automatically, or you might have to go to Communications Configure and specify your COM ports and baud rates. Hopefully it connects automatically. We'll get into troubleshooting communication problems later on, but right now I'm communicating with my 19 plus V2. I clicked in the window here, I'm hitting the return key, and I can see I'm getting a response. I can send commands to the instrument, and I'll get a response from it. Sometimes CTerm does not populate the send commands window, and that's okay. Normally, this fills in with all the commands that apply to your particular instrument's firmware version. If it's not populating, what you can do is go to File, Load Command File, and then within the program files for CTerm v2, there's a list of command files in XML format. So we're going to open the 19 plus command set.xml, specify that we're using firmware version 3.1 and click OK. From there, it's going to populate this send commands window. So if I don't know the commands that apply to this instrument, I can look in this window and say, yes, I would like to get this configuration data in XML. That tells me that command is get CD, click on execute, and it will automatically do that for me. Another useful feature in CTerm v2 is the ability to create what's called a capture file. What this is going to do is create a text file of everything I type into the window here and everything the instrument responds with. So I highly recommend creating capture files before you deploy this instrument, so you know the configuration of the instrument before it went out in case you encounter any problems. If you ever work with our technical support team, they will often ask you to create a capture file with a specific list of commands in order to get the information they need to know how to troubleshoot your instrument. So I'm going to go through a couple of commands. The first one I like to send is the DS command. I believe this stands for display status, and this will give you a nice summary of the full configuration of your instrument. So I know things like the serial number here, the current time and date setting, my battery voltage. In this case, I'm applying 12 volts, so it's registering this at about 11.3 volts. The battery voltage of my backup battery. And then how many samples I have in the memory, and just some general stats on the instrument. We'll get into a little bit more of this later, but you can also send status commands like get HD. That gives you the hardware information of your instruments. This is useful for technical support. Get CD sends you similar information as the DS command. Get SD, which sends similar information as the DS command. And then you can also change settings. So if I want to change the date time, I can send the command dates time equals, and then the format is month, day, year, year. So I'm going to say 10 for October. Today is the 5th. 05, it is year 2021. And then let's just say the time is 000000, hour, minute, second. So now when we look at that, it says that the date is midnight on October 5th. So that's how you change that. You might be hearing this pretty awful sound that the CTD is making. That's actually the pump running. And then so you can send the command pump on your instrument, and then pump off, turn it off. Word of warning, these pumps are not meant to be ran dry. So if you're going to be testing it for any extended period, more than a couple of seconds, I would recommend taking some deionized water and just squirting it into the pump head so it's lubricated by water. It's not going to be as loud, but it might splash some water everywhere. On top of that, you can also send the TS command, take sample. And that's going to take a sample and output it in the specific output format you have currently enabled. So in this case, we have our output format is raw hexadecimal, and that's what this is here, a string of hex data. We can also change the output format to converted data. The TS command. And that's going to tell us temperature, conductivity, and pressure of this room right here. So room temperature is about 21.47 degrees C. Conductivity is 0 because this is currently in air. You can change a lot of settings in CTerm, but the takeaway is this is how you communicate with your instruments, change settings with these commands, and create a log of the current status of your particular instruments. As I mentioned before, you also have your on-off switch. So when I flip this switch to on, momentarily, we'll start seeing data streaming into CTerm. So in this case, if you were using a data logger or something that's collecting data in real time, it's connected through RS-232. This is the data that it would be seeing. Because we've specified output format 3, we're seeing converted data. But if we go back to output format 1, or I'm sorry, 0, and we'll see the same thing, but in hexadecimal format. This is the format that the CSAVE software requires in order to interpret data coming from the CTD. Now, on top of that, this is sort of terminal stuff. You can do the same thing with TerraTerm or PuTTY, but CTerm also has some useful tools, such as the ability to upload data from your CTD. In the case of CTerm, uploading the data will create what's called a .hex file. So I want to save it in Siebert University, like that. In this case, you can upload it as text or binary. Binary is faster. And then you have your options. You can upload all the data as a single file, all data separated by cast number range, or from a single cast. So let's say cast number 8. That's the one that we just did. And then click on upload. CTerm is automatically going to send all the proper commands to the instruments. And then start uploading the data. The end result that we will have is a hex file. So these are the files that we just created, a hex file and an XML file. The hex file is ultimately what we want. You can open that up in Notepad, or I like Notepad++. And within your hex file uploaded from CTerm, you're going to have a bunch of information about your particular instruments. Basically, all of those status commands are captured in the header. And then after that, you'll have all the data. So this is the data that we just captured on the bench right here, 2 minutes after we changed the time. So we can then take this file and process it in Siebert Data Processing. Siebert Data Processing is going to be able to interpret these samples and convert them to temperature, conductivity, pressure, and any derived parameters that we have beyond that. Okay, so that is a pretty quick run through of CTerm v2. You can do a lot more with this. You can configure this instrument to work in Mord mode. And one of the more important things you can do with this is set it up to accept different auxiliary voltage sensors and log the data to memory. When you do that, you need to change the configuration file of your CTD, which we're going to demonstrate right now. Okay, so the configuration file that I mentioned is in the .xml-con format. This is called your xml-con configuration file. This is used by CSAVE and Siebert Data Processing, and it contains the CTD settings and calibration coefficients for all of your sensors so that the software knows how to take that raw hexadecimal data and convert it into engineering units. At Siebert, we generate these for you whenever you get a new CTD from us or send your CTD back for service and calibration. We will send you a new XML-con file that has all of the new calibration coefficients and configuration of your CTD. That's important to know because XML-con files are completely external to the CTD. Your CTD doesn't create a new XML-con file. when you change settings in CTerm. You have to manually go in and change your XML conf file. So it's very important that you change the XML conf file when the CTD configuration changes. Failure to properly do that will either A, prevent you from processing or visualizing your data in the first place. That's the best case scenario. Or B, actually process your data with incorrect calibration coefficients. And you might not notice. The changes will be subtle, but they will be incorrect data. So it's very important that you modify your calibration, or I'm sorry, your configuration file to reflect the instrument's proper calibration. Okay, so we're going to take a quick look at that. So configuration files are not necessarily the most intuitive thing. And what we've got here is actually, I'm going to pull this over here, change my screen. This one. Okay, Kim and Lindsay, can you see this screen now? It should be showing the whiteboard.
Yes.
Okay, great. So what we're going to be going over here is how to create an XMLCon configuration file. That's this guy right here. So this configuration file is correct for the particular CTD that I have. The temperature, conductivity, pressure, and oxygen calibration coefficients are correct. And all the settings match here. But say that you need to create a new configuration file because you've just installed an oxygen sensor on your instrument. The steps to do that are somewhat convoluted, but you can figure them out when you know what to do. So say we have a CTD and we just plugged an oxygen sensor onto connector J2 as I have here. When we look at the pin diagram of J2, we see that we have voltage 2 signal and voltage 3 signal on the J2 connector. And so what that's going to mean is our oxygen sensor is either putting data onto voltage 2 or voltage 3. Now, in order to identify which channel it's putting the data onto, we need to look at the cable we're using to connect our sensor to our CTD. So in this case, I've looked up the drawing for the cable. You can do that on our website with the cable search tool. If you pull up the drawing, it's going to have this pin diagram here. That's going to tell you which pins on my oxygen sensor are connecting to which pins on my CTD. So with the oxygen sensor, I know that pins 2 and 3 are oxygen data. Those are going to pins 2 and 3 on my CTD. So if I go over here, I know I'm connected to J2. I'm going to look for pins 2 and 3 on the connector, and that's telling me I am outputting oxygen data on voltage channel 2. So then what I'm going to want to do is go into CTerm. And determine which voltage channel is currently connected. Now, I've pre-configured this CTD to already work with the oxygen sensor, but when I send the DS command, I see external volt 0 is no, 1 is no, 2 is yes, 3, 4, and 5 are all no. So this is already configured to accept data from my oxygen sensor. But say that these were all no, and I needed to identify which channel to put this onto. This is how I would do it. I know I'm using this cable, plugging it into this connector. That's putting the data onto voltage channel 2. I then have to go into CTerm and send the command volt2 equals y for yes. And then doing so will change the scan length, which is going to erase all of these samples on the memory. So that's OK with me. 2 equals y. In that case, when I send the DS command, I'll see that volt2 is yes. It already was. If I say volt3 equals y, repeat, the DS command, I see that now voltage channel 3 is also yes. I don't want that because I don't have a sensor on that. I'm gonna disable that. Send the DS command and go. Okay, so I have my one sensor and my one voltage channel enabled on the CTD. Now, next thing is to create the XMLCon configuration file. And in order to do that, this is where it gets a little bit convoluted. So I know that voltage channel 2 is enabled on my CTD, but when I go to modify my XMLCon file, I have one external voltage channel enabled, and but it gives me options to go up to 6. When you have 6 enabled, it labels them as voltage 0, 1, 2, 3, 4, and 5. So intuitively, you might think that I want to enable this as my oxygen sensor. But in reality, that's incorrect. If you have 6 external voltage channels enabled on your XMLCon file here, it's going to think that you have volts 0, 1, 2, 3, 4, and 5 enabled. If you don't have those enabled, this XMLCon file is not going to match up with your CTD's configuration, and you won't be able to process your data. So in reality, what we want to do is say we have one external voltage channel enabled and specify that that is our oxygen sensor here. So even though this says AD voltage 0 and our oxygen sensor is on external voltage channel 2, what's important is that the order of sensors matches the order here. So say hypothetically we had an oxygen sensor, a chlorophyll sensor, and a turbidity sensor, where oxygen is on voltage channel 2 and chlorophyll and turbidity are on channels 4 and 5. What we would want to do is say we have 3 channels enabled and then have the sensor on channel 4 listed as chlorophyll and turbidity. Is well, let's just say it's a transmissometer and turbidity. We put our chlorophyll and turbidity channels on AD voltage 1 and AD voltage 2. So what's important here is that the order of sensors connected on these external voltage channels matches the order of sensors in your XMLCon file. So in this case, we have our oxygen sensor. That's the only one we have installed. So we can say, yep, save that and end. What happens if you don't have that properly enabled is CSAVE and CBER data processing are not going to be able to process your data, because when you enable additional voltage channels in your XMLCon file, it expects a longer scan length here. So as we saw in CTerm, when we have raw hex data and we send the TS command, it spits out a string of data that is a very specific length. If we enable another voltage channel, we're going to see that we have 4 additional characters at the end of the string here. And our XMLCon file is not going to know what to do with those additional characters, and it will fail to process your data. So in this case, we can look at this data string and actually break it out into specific strings of data. So the first 6 characters are your temperature data. The next 6 characters are your conductivity data. And the next 10 characters are your pressure and your pressure temperature. So it's temperature, conductivity. And then any additional voltage channels you have enabled will add 4 extra characters at the end of your string here. So if you're getting what's called a scan length error, which we'll see in CSAVE, you can go ahead and look at your data strings coming from your CTD and identify how many voltage channels do I have here. If we had, say, another 8 characters at the end of this, that would imply that we have 3 voltage channels enabled. Volt 2, this could be volt 3, and this could be volt 4. In this case, we don't have that. So we know that this is voltage channel 2, which corresponds with our oxygen sensor here. So once you've got that in your configuration file, what you want to do is double click on the instrument itself and then load in the calibration coefficients for this particular sensor. And now we can help you with this at Seabird. You don't have to type all of this in manually. If you have a file that contains the calibration coefficients, you can click on the import button, and it's going to import, you'll be able to import the calibration coefficients into this, click OK, and then click Save, and your XMLCon file is ready. What's important to do from time to time is go through and look at the calibration coefficients in your file here and cross-reference those with the calibration certificates you get from Seabird to make sure that these are still correct and the most up-to-date calibration coefficients for your particular instruments. I'm going to stop sharing that back here. Okay, so we've talked about CTerm, we've talked about XMLCon configuration files. Now we can talk about CSAVE v7. This is the data visualization software for Seabird CTDs. You might see this used a lot with the 9+ CTD. It can also be used with the 19+ v2 and other profiling CTDs. It can also be used to control water samplers. And it's a highly configurable software that you can use to visualize the data coming from your CTD in real time. This is the view. You might be familiar with this. Prior to connecting your CTD to CSAVE and getting real-time data, you need to set it up and configure it. So what I typically do is connect my CTD to CTerm, configure the baud rate, the output format, the sampling mode, and then I'll close CTerm, connect it to CSAVE, and then configure the inputs here. So using the same COM port that I had connected to CTerm, the same baud rates, data bits, and parity. And then I'll want to load in the XMLCon configuration file that I just made. If you're using a water sampler, which I'll talk about on Thursday, this is also where you would configure that to accept data from the water sampler and control it. Beyond CSAVE, we also have Seabird data processing for taking that hex file that we uploaded from CTerm and converting that into a .cnv converted data file. This allows you to select what kind of data goes into your converted data file. There are a lot of advanced processing modules where you can take that basic temperature, conductivity, and pressure data and really optimize it to clean up any dynamic errors that you might encounter, and really optimize the data set for use for your research. I'm only going to talk about the first module, the data conversion module, where you take your raw hexadecimal data and get it to converted data formats. So CSAVE, Seabird data processing, both use your XMLCon file, and we're going to demonstrate that right now. So first thing I'm going to want to do is in CTerm, confirm that I'm outputting raw hexadecimal data, which I am, which is the format that CSAVE requires. After I've done that and confirmed that my voltage channels and everything match up with my configuration file, I'm going to close CTerm because it's currently occupying the COM ports, and you can only have one piece of software talking on the COM port at a time. Next, I'm going to launch CSave, and this is the view that I've set up for myself. And the first thing you want to do is click on the Configure Inputs button, which is going to open up this window that we saw in the PowerPoint. This instrument configuration tab is telling me this is the file, the XMLCon file I have loaded into this. So I want to load in the file that we just worked on. And then I'm going to open up this serial ports tab. This is where I can specify the COM port that I want to use to communicate with my CTD, baud rates, data bits and parity, etc. And then if you're using additional things like a water sampler, serial data outputs, and a remote display from your deck unit, this is where you'd specify that as well. But we're not going to do that now. We just care about the CTD serial ports. Okay, so now CSave is presumably able to connect to our CTD. And what we can do is log some real-time data here. So if I click on the real-time data button and click Start, it gives me some options. I can begin archiving data immediately or set these different options. I'm going to always archive data immediately. What that will do is create a hex file based on the data that CSave is receiving. So I'm going to set this output data to Seabrook University data and call this CSave. If the configuration file I loaded in at the configure input spot is not correct, I can always go through and configure that again here, but we know that we already have that. So I'm going to click Start. You can add some notes that will be added to the header of the file. And then it's going to start the acquisition. Now, this is a countdown timer saying CSave is waiting to get data from your CTD. And so in this case, my CTD isn't outputting anything until I click the switch to on, at which point it's going to start outputting some data. Once that countdown timer goes away, then the data is being received by CSave. And as long as your XMLCon file is able to interpret that data, you'll start to see that coming in. So you'll see in this case, I have a scroll display that's showing all of the samples that are coming in from my CTD. And in my plot displays here, I can see the data coming in. You can do things like modify the ranges. So in this case, this has depth on the y-axis, but since we're not doing a profile, I'm going to look at pressure on the y-axis and time on the x-axis. And this is showing me all of the data I have coming in from this CTD into CSave. Not very interesting. This is basically telling me that in air, the room temperature is around 21 degrees C and there's zero conductivity. So that's pretty much as we would expect. Depending on the sensors you have enabled on your CTD, you can select a bunch of different things here. And pick which variables you want to look at. So these are all of the variables that you have measured by your CTD currently, and everything you can derive from those variables. For example, we can derive density from temperature, conductivity, and pressure. And we can add that to our plot here, at which point it's going to start outputting that into the plot. Not very interesting because we're measuring this in air. If your CTD is connected in real time with a C cable or with a long RS-232 cable, this data is going to be a lot more interesting. And what you might see is when you click stop, the profile you get, you'll be able to identify things like the thermocline, the halocline, and if you have it connected to a water sampler, you can command the water sampler to collect water at specific spots based on the real-time data you're getting from your CTD. This also has the ability to replay archive data. So if you click on the archive data button, click start, you can select a data file. So let's just select a random one here. Open the correct configuration file for that archive data. And then CSave is going to replay that data into the plot displays that you have here. Once again, you can modify things to look at, say, density based on what you're interested in. And you can modify the ranges of this. So CSAVE is both a real-time acquisition software and also a way for you to visualize data that you've collected in the past. Okay, next we have Siebert data processing. And again, I'm only going to go through the data conversion step, which is going to take our raw hex data and convert it to a .cnv converted data format. So as you can see, there are a lot of different modules, but we're just going to talk about data conversion. And in this, we want to select the configuration file. Actually going to navigation. Select my config file here. And then select one of these hex files here. And then in the data setup tab, you can select your output variables. So I currently have this set to output all temperature, conductivity, pressure, salinity, depth, etc. If I want to look at raw oxygen voltage, density, plume anomaly, whatever I want, I can specify that here. And these data will be displayed in this order in your converted data file. This can tell me if I want to skip over scans at the beginning of the file. I do not. And then this is saying process all the data in the file. So in this case, I'm going to output this to Siebert University data. Okay. Okay, and it says processing complete. So now when we open up that file, we can see we have a .cnv file created. Today. So this is the CNV file that we just created. It retains the header uploaded from the hex file. And then it tells us these are the data that we have in our columns, and this is the order that that data will appear. And then this is the converted data that we got out of Siebert data processing. So based on the calibration coefficients in our XML file, the data collected by the CTD, we created this converted data file that contains all of these variables, which you can then visualize in different Siebert data processing modules. You can also apply advanced correction to this data, and you can also export this to Excel, MATLAB, what have you, for processing outside of the Siebert suite of software. Okay, so in the final steps here, I just wanted to go through a couple of troubleshooting and tech tips. So different things that you might often encounter with the 19 plus V2 is a low conductivity or salinity, which often means that you need to clean your conductivity cell. You might, from time to time, not get communication from your CTD, and I'm going to walk through a couple troubleshooting steps from that. You might not get a signal from your sensors, such as the SBE43 that we have connected here, which might mean you need to troubleshoot that sensor, you might need to troubleshoot the CTD, or you might need to identify the proper cable to use. And finally, depending on your actions within CTERM, you may have lost a couple of samples. And depending on how what you did after that, you may be able to recover those samples. So the first thing I want to demonstrate here is how to clean your conductivity cell. This is both kind of general maintenance, something that you'll want to do here and there, and also something that you can do if you're encountering a low conductivity signal. We have an application note that teaches you how to do this, but for the most part, it's pretty straightforward. Essentially, you want to take a surfactant such as Triton X or any other kind of non-ionic detergent, and basically just rinse that through the conductivity cell. So let me raise this camera up a little bit. This bottle is filled with a 1% solution of Triton X, and the rest is DI water. And this is part of the cleaning kit that comes with your instruments, a plastic syringe with tubing that fits onto the end of your conductivity cell here. So basically all that we're really going to do here is fill this syringe up with our dilute Triton solution. Connect it to the end of the conductivity cell on this hose barb attachment, and then run it back and forth. What we're going to see is you get a lot of bubbles in this tubing here, and you'll see bubbles moving through your Tygon. That's good. And you're just going to want to agitate that back and forth. And what this is going to do is help remove any biofouling or maybe oil that's built up inside of that. And then it's going to travel through the plumbing and out the pump. So you might need to do this a few times depending on the state of your instruments. And then after that, what you'll want to do is fill this up with deionized water. And rinse all of the soap out of this plumbing. Now, something you can also do that I like to do instead of this step is you can submerge your CTD in clean water and then start running the pump. If you connect it to CTerm v2, you can send the command pump on, which is going to turn the SBE5 pump on, and it'll start pulling water through the plumbing. That's going to pull that clean water through the CTD's plumbing, and then pretty quickly flush out all the bubbles from the Triton X. If you can't do that, this step can often take a long time. You're just flushing a lot of soap through the system and just trying to get it out as much as possible. So make sure you're catching this in a basin. And try to empty as much of the Triton X out of the CTD's plumbing as possible. What you'll often find is after you go through that cleaning procedure, your conductivity signal will probably increase a little bit back to what it was when it was first calibrated by Seabird. Okay, next we have this problem where you might have no communication from your CTD. And in that case, it's useful to run what we call the loop back test. Now, this test is to determine whether or not the cable you have connected to your CTD, the data I/O cable I've got right here, is actually sending data to CTerm. That will ensure, if it passes, that you have the correct COM ports and your cable actually works. So what you can do is pull out your cable. If you look at the diagram for the data I/O cable, pins 2 and 3 in this, and you can kind of see it if you look in there. Pins 2 and 3 are the RS-232 receive and transmit pins. And so if you bridge those two pins and launch CTerm, you will get essentially signals sent from the transmit part of the pins and signals received into the receive pin. CTerm decides to launch. So in this case, I have a paperclip bridging pins 2 and 3 right here. And when I type characters into CTerm, I see that they appear. When I remove that paperclip, I type things into CTerm, they don't appear. So what that does is it tells me this data I/O cable that I'm using here is working just fine. The COM port I have connected to CTerm is working fine. and the USB serial adapter I have is working fine. Now I can troubleshoot communication problems specifically with the CTD. At that point, I would recommend applying external power to your CTD. It's possible it's not talking because the batteries are dead or there are no batteries installed in the instrument. And then also troubleshoot, make sure that your data I/O cable is plugged into the right spot on your CTD's connector. And also make sure that you're connecting to your CTD at the proper baud rate. If you are connecting at the incorrect baud rates, data you get from your CTD might just be garbled. The characters you see will be unusual. It'll look like garbage. What that means is your CTD is maybe communicating at 9600 baud, but you have CTerm configured to communicate with CTD at, say, 2400 baud. So you could try different baud rates until you get something that looks a little more like standard CTD data. Okay. Now, if you have an auxiliary sensor plugged into your CTD and you're not getting any data from it, there's a couple of things you can do. You can troubleshoot your sensor, you can troubleshoot your cable, or you can troubleshoot the CTD. And one thing I like to do is pull the cable off of the CTD's connector and run a couple of tests. The first test is to take a voltmeter and determine that my CTD is actually sending data to the sensor. So I'm setting my voltmeter to measure DC volts. Now the connector on your CTD is meant to output, I think about 14 volts to any auxiliary sensor, power it. And if it's not doing that, your sensor's probably not even turning on. So I'm going to flip the switch to on, and then measure the voltage on pins 1 and 6 of my CTD, and see that it's sending out, in this case, 10.75 volts. Yep, 10.8 volts. So I know that my CTD is on, and it should be sending this voltage to my auxiliary sensor. Next thing I can do is I can simulate the data from the sensor using a AA battery. Because these sensors are outputting a standard voltage, that is, they are supposed to be outputting a 0 to 5 volt signal, and I can measure the voltage from the CTD with this command TV. That's telling me the voltage from all of the sensors currently connected to the instrument. I can simulate a sensor by connecting a AA battery to the pins that are supposed to be receiving data from this sensor. So as we looked at before, I know that pins 2 and 3 are supposed to be getting data from an oxygen sensor. So if I connect the leads to pins 2 and 3, send the TV command, and then connect my battery to it. I have this reversed. This is kind of hard to do with one person. I should start to see voltage on these pins here. And it's possible I'm not connected to the right spot. So I might want to look at the connector diagram. Okay. Okay, let's try this one more time. Okay, we're kind of running out of time here, but essentially, I should be seeing 1.5 volts on one of these channels when I connect the battery up to this. I apologize, my battery might not be live, or I might not be connecting my leads properly. But essentially, the step is to simulate an auxiliary voltage sensor sending data to the CTD by using a battery that's outputting 1.5 volts. Since we know it's 1.5 volts, if we see 1.5 here, then we know that it's getting data from the sensor, or it should be getting data from the sensor. And at that point, we can troubleshoot the sensor itself. Okay, and then last thing we can do is when you send the DS command, you can see how many samples are currently in the memory. But say you accidentally deleted all of the samples in the CTD's memory, but there's still some samples that you wanted to recover. The memory of the CTD is more like a VHS tape than it is like a flash drive, where when you reset the sample counter back to 0, it's not deleting all the data in the memory, it's rewinding it back to the beginning. So what you can do is fast forward the tape back to where you think that your samples were and upload your data again. So in this case, I'm going to send, we have 2,801 samples here. I'm going to send the volt3 equals yes command, which sends us a message. This command will change the scan length and or initialize logging. Initialize logging means reset the sample counter back to 0. So when I send DS, I can see that my sample is now 0. Now I can send this command 208. Sample number equals 1208. Again, it'll say this will change the scan length and initialize logging, repeats. And now when I send the DS command, I see that it says it has 1208 samples in the memory. Now, that essentially, by initializing logging in the first place, we rewound the tape back to the beginning. And by setting the sample number to 1208, we fast forwarded it back to that spot. From this point, we can go ahead and upload our data again. And it's going to hopefully upload data from the CTD up to the point of sample number 1208. What we're warning here is because this is like a VHS tape, if you were to tape over the samples, say you reset logging back to sample 0, you log some data and then stop logging data, it's going to record over those previous samples that you had in the memory and prevent you from recovering data like this. So this is a trick you can use, especially if you have a ton of samples in memory, to hopefully recover some of your data. But it's not foolproof. It's not to say that these samples are always in the memory. If you overwrote them, they're gone forever. So be careful when you initialize logging, and always make sure to upload your data as much as possible. Okay, so that's pretty much what we have prepared. I apologize for any technical difficulties we had here. But why don't we take some time to go through the Q&A? Kim, do you have anything lined up on deck?
Yes, I do. Okay, so let me go up here. The first question that we had here was that they have to be alkaline batteries. So some of our other instruments use lithium-ion C cells. It would be easier. So no, we don't use lithium batteries with these, but we do have an option for rechargeable nickel cadmium batteries. I don't know, Greg, if you want to add anything to that.
Nope, that's correct. So no lithium ions with the 19+V2 at least, but there is an Ikeda rechargeable battery pack. In general, we recommend alkaline batteries, and I always recommend changing your batteries as often as possible. Batteries are cheap and data is priceless.
Okay, the next one is the data set in real time the same as data stored on the SBE 19 plus V2 internal memory? Okay, so yes, if you are able, so a lot of it depends on what the actual transmit rate of the sensor is. So if you're using a serial cable that's really long, your baud rate's going to be a lot slower. So you can't actually use the full 4 hertz. So you're gonna have to average, and then you're gonna have to send it to the real time. And so the instrument will store the exact same hex file as that average data that it's sending to the computer. If you're able to use a deck box, you can get that. It has really fast transmission rates, and you're able to get the full 4 hertz sampling, and you will have the full 4 hertz both on your computer attached to the deck box and the instrument itself. Oops, I disappeared there. All right.
Yeah, one thing I want to add to that is the data format is the same as what you collect live in CSAVE, this hexadecimal format. I think these are 2 different casts, but it's a good example. Say this is a hex file that we uploaded from the memory from a cast we did in CSAVE, and this is a hex file that was written by CSAVE. The data you have here is going to be the same. However, the header is going to be much more verbose from the data you upload from the CTD versus what's written in CSAVE. CSAVE isn't doing this automatic thing where it's sending all the status commands and writing those to the header of the file, but it is collecting the data. CTerm, when you upload data, is going to do that. So this provides a lot of useful information about the calibration coefficients on the CTD, the configuration of the CTD. That's useful for troubleshooting in the future or just keeping a record of your instrument.
All right, next one. Sometimes when I select my con file as well as the corresponding hex file and press start process, nothing happens. All right, and it says processing stop. So what this problem means, and I think Greg kind of touched on this a little bit, is that you actually have to make your con file match what's being sent out by the instrument itself in the hex file. And so we call this a scan length error. So this means that your con file doesn't match the data that's actually being produced by your instrument, and the software is expecting like a certain amount of hexadecimal lines, characters, and it's getting less of them. And so the best way to do this is to actually just click on your .conf file, double check which ones you have on there, and also talk to your instrument with the DS file. So if you have like 3 voltages enabled and you only have 2 voltages on your con file, that is typically a hex file. If you're a little bit more of an advanced user, one thing you can also do is if you look in the manual, you know, like your temperature, your pressure, and your conductivity each have a number of characters. You can count all the strings and kind of figure out where you are in that as well.
So that's part of what I demonstrated with creating the XML con file here. We know based on this string that we only have 1 voltage channel enabled, so we need to have only 1 voltage channel enabled in our XML con file. So here I just made an example XML con file that does not match the configuration of this hex file, which has 1 voltage channel enabled. However, I loaded in this XML con file that has 2 voltage channels enabled. So when I click start process, it's going to say processing stopped, and it's not really going to tell us why. So that's where you need to do some troubleshooting. It's almost always the fact that your hex file does not match your XML con file, at which point you should go in, try to identify in CTerm the configuration of your CTD, and then make sure that your XML con configuration file actually matches that config, and then you'll be able to process your data.
Right, the next one. How often, so Greg showed of cleaning, and how often do you do this cleaning? That's a really great question, and I really think a lot of it depends on your application. I typically recommend for the 19 plus in particular, because you're typically using it off small boats in coastal regions. You definitely want to just give it a quick rinse off after a day in the field. There's just like a lot of murkiness and stuff can get in there, and it's just really good practice to keep that clean. And it's really easy to get it off if you just kind of have a bottle of the solution in your kit. You have one of those syringes, give it a couple swishes at the end of the day, and do that. That being said, that sometimes like you're working in a really muddy area, there's a lot of seaweed and there's stuff floating on the top, just check it out. Maybe you have to do it a little bit more. You can see that your data quality might go a little bit down as you're looking at the real-time data. But if you think it's like really gross, then I would suggest maybe like halfway through the day, give it a clean too. All right. Okay, I have the next question. Let's see, I'm going to skip this one. Okay, how do you normally store the CTD, with the dry conductivity cell or soaked? Okay, so there's two ways to do this. So if you are doing long-term storage, we recommend that you clean it and then you store it dry. You want to make sure that you're taking your 19, giving it a couple good shakes to actually get all the water out, and then kind of close up the tubes. We usually send it with a bunch of Tygon tubing, just so you don't get any dust in there. It's not necessarily, it's if you can just close off one of the ends, that works too. If you're doing it for short term between casts, to get the best data, we do recommend that you store it with a little bit of DI water, but this isn't necessarily the case for all that. That's typically if you really need high accuracy kind of for the 911, so that's like the big shipboard system. So just make sure that but if you do need that high accuracy, depending on using 19, you do want to do it dry. There is an application note. I don't remember it off the top of my head. Maybe Greg does, that does that, and I'll drop that in the chat.
Yep, I think that's app note 02D. Kim, if you could put that in the chat, that'd be great. I see this question, is the 19 plus V2 memory a ring memory? If I'm understanding that properly, I think a ring memory is something where once it fills in the memory, it overwrites the samples at the beginning. It does not. The 19 plus V2 will not overwrite any samples on the memory. Once you fill up the memory of the instruments, it will still output data in real time, but it won't save anything else to the memory. So always make sure that you're uploading your data and then initializing the memory as often as possible. It can hold quite a bit of data, but you don't want to lose anything. Please let me know if that is an incorrect interpretation of your question.
Okay, the next question that we have, where is SBE in its efforts to update or replace its software package? That's a great question, actually. Yes, we are doing that. We're redesigning the software. We're in the process of doing that. We're doing some testing with users, and we're always actually also looking for more software testers. So if you would like to do that, you can ping us in the Q&A, and someone will take down your name, and we'll contact you. So we're kind of doing rolling testing along. So there's different kind of stages in the process that you might actually see the software. And we always accept user input because you are all the people that are using it most in the field.
Okay, question. If I always externally power the 19 with an SB33 deck unit and a C cable, can I remove and run without the D-cell batteries? Yes, you can do that. And some people do. Some people prefer to run it without the batteries. Leaving batteries in here for long term is risky. They could leak and damage the instrument. One thing to note is that the batteries in the instruments maintain the real-time clock. Once those are taken out, there is a backup battery soldered to the board on the 19 that will then be drawn on to maintain the real-time clock. And you don't really want that to run out. If it does run out, then the clock is not going to be able to maintain itself. We will replace that at Seabird when you send it in for service if it seems like it's running low, but it just could be really inconvenient to have that die. So it's sort of a give and take of whether you want to leave batteries in. I find that to be helpful for testing process. If you're just testing a CTD to go out into the field, it's useful to know that you can talk to it without plugging it into an external power supply. But it's totally up to you. If you're always running it with external power, you can certainly remove the D-cell batteries. Another question, can you download the 19 plus V2 memory with a USB cable like other profilers? You cannot. This is only able to upload data via RS-232. You can increase the baud rate on this quite a bit to really speed up your data transfer, but currently the 19 plus V2 does not have USB uploads. And by USB uploads, I mean a USB connector built into the CTD itself. It doesn't have that.
So I think that may be it in terms of our questions.
Okay, great. Awesome. Well, thank you everybody for attending. Apologize for any technical difficulties we had with the video. I hope that everything was clear for you. Please let us know if you have additional questions, and please join us for the additional modules we have in Seabird University. Lindsay, do you know if the survey was posted into the chat?
No, but I can do that right now.
Okay, great. So we're going to post the survey into the chat. We'll also put that survey onto the SBU 2021 landing page on our website. We would love to hear from you on what topics you would like us to cover. If you want to know more about the 19 plus V2, some stuff that we couldn't fit into an hour and a half, please let us know if there's specific topics. If you want to know more about different product lines that we offer here at Seabird, or just general training for certain applications, we want to know. If no one else fills out the survey, it's possible that you'll get a private training just for your own application, so I highly encourage you to do it.
So I just shared in the chat, that is the link for future Seabird University topics. So please feel free to fill that out if there's anything you think that was missing this year. But bear in mind that we are having additional courses, as Greg has mentioned, throughout the month of October. So thank you everyone for your participation, and looking forward to having you at future sessions.
All right, thanks again, everyone. Have a good morning, afternoon, or evening, or night, depending on where you are.
Yep, thanks everyone. Have a great day.
Thank you.
See you soon.